Hello, CIS40A. In this video, I'm going to talk about Chapter 3, which address TCP IP, and it talks about addressing and how to use IP address. For this video, we are going to cover the notes and the assignment, so it will be best if you follow along with the notes and the assignment. So as we recall, in the prior week, we talked about TCP IP as Transmission Control Protocol and Internet Protocol. This is used for our network today, and that's what makes the internet. And TCP IP is going to allow us to implement network servers, systems, and handheld devices using IP address, which is connectionless. And this particular protocol is Internet Protocol, and it's used for addressing. TCP is going to be able to give us the reliability in transmission. The name Transmission Control Protocol, it actually established three-way handshake in order to make sure that communication is established before data is sent. So in this chapter, we're going to focus on IP addresses. And IP address with the version 4, you will see on page 1 here, it talks about the IP version 4 address contain 32 bits, and that would refer to as octets for each of the values that's before the period or the dot. So each of the octet would be 8 bits, and so when we have 4 octets, we would have 32 bits. So the 4 decimal values are going to be representing the IP address, and it would be separated by the dot or the period. And we would use decimal values here, and the system will convert that decimal value to the binary. So using the IP address, we also need to implement what's called Subnet Mask. And with the Subnet Mask, it's also represented with another 4 octet, but usually you would see that it would be 255 to start and following either 0 or 255. And that would be equivalent to what we see as a zip code in a city, where the subnet mask is going to allow us, the system, to identify which part of the network it is using. So here, the subnet mask gives us the network ID and the host ID. And the network ID is normally represented with the 255 values or 0 values. So what you would see in the addresses, for example, in this case, 192.168.1.15, this is a Class C address, and it would have 255, 255, 255, 0. And that would means that the first 3 octet would be the network ID. So when we look at the first 3 octet, that will be the network ID, and that's how it's able to identify which network that system belongs to. So now the network ID assigns a unique address to the network itself, so while the host ID is unique to the system. So the network ID tells us which network, and the host ID, which is in this case the last octet, is going to represent the value for specific system. And there will not be a host that would have the same exact IP address, because every IP address is going to be unique to each system. So going to the assignment, we would answer the first question: how many bits are in the IP version 4 IP address? And that will be 32 bits. And how many octets are in IPv4? There will be 4 octets of the IP version 4 address. And how many bits are in each octet? There will be 8 bits. So when you have 4 octets and each octet is 8 bits, that will give you 32 bits for IP version 4 address. Then in the next question, it asks you to determine the network ID for the following address and subnet mask. So the first IP is 192.168.0.100, and the subnet mask is going to be 255.255.255.0 because this is a Class C address, and traditional Class C address you would have the first 3 octet would represent the network ID, and based on the subnet mask, when you see 255, that will be the first 3 octet as all the bits are on, and all that bits are on represent the network ID. And then on the next octet, also 255 for the subnet mask. So that would also be the network ID here. And then for the last octet, which is this right here, that would also be a network ID. So in the Class C address, we would see that the first 3 octet would be the network ID, and the last octet would be your host ID. So we would know that it would be network, 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 and host. For 2B, when we look at the IP 10.0.0.1 with the subnet mask of 255.0.0.0, as all the bits are on for the first octet, we would know that the first octet here, the 10, would represent the network ID, and the rest would be your host. So for B, we would know that 10 is the network ID. Question C, 172.1.1.1, and this is a Class B address. As in Class B address, we would have network, network, host, and host. And in the Class A address for the prior question, there will be network, host, host, and host. So what you see here is for C, the first 2 octets, those are going to be all the bits are on. So the subnet mask is 255.255.0.0. So that means that the first 2 octet of the IP address identify the network, which is 172 and 1. That would be the network ID for question C. In question D, we have 10.10.1.106. And when we look at this subnet mask, we would see that the 255, that would represent the first octet 10, and then 254, that will be the next octet. So while this is not 255, but most of the bits are going to be on here, that would represent the network ID. So you would have the first 2. Now, if you look at the first octet and you ask, why is it 10 and it's going to be in Class B address? Because if the subnet mask is using the second octet as also the network ID, in this case, that means that while it's using the first octet in Class A, it can also be using Class B address if the subnet mask for the second octet, all the bits are mostly on. So what we would see is that our 10 and 10 in the front here would represent the network ID for this particular address. So you would refer to the subnet mask, and the values that would be 255 or 254, 252, you would see that that would represent the network ID. Then in the next question, it asks you, if a computer A is sending data to computer B, how does computer A locate computer B in the network? The computer A would use the subnet mask to determine computer B whether it is on the same network by comparing the network ID. So it would look at the subnet mask like a zip code. If it is in the same zip code, it would know that it is in the same network. So if the subnet mask is the same, then we would determine that it is in the same network. If the subnet mask is different, then it would need the router to be able to route to a different network, as it would not be able to identify itself with the other system in that network. So it would compare the network ID using the subnet mask to determine where that system would be for the destination. And for question 4, it asks you to send data in the same network, what configuration is needed to send and receiving system? You would need a system IP address and the subnet mask. So when you configure IP address as we do in the lab, it would also include a subnet mask, and that subnet mask is going to be used to compare to see if that system exists within the same network. If the subnet mask says that it's a different network ID, then it would then forward it to the gateway, which would format it for the external network. So in your notes, it goes over some of the details on how you can look at your IP address. So here we have 192.168.1, and that will be network, 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 and the last digit will be your host ID. That means that this particular address, network, and any other system in the same network will have the same network ID, meaning that it would have 192.168.1 to really be in the same network, and the host number will be different. So I can have something like 192.168.1.16, and that would make it in the same network, or 192.168.1.23, that would also be in the same network, as the first 3 octet is the same as the sending system IP here. So as you can see, that's how it's going to be able to determine, as long as we would have the subnet mask that would be exactly the same to the other one. Now, another example you would see is that when the subnet mask is used, such a system as 192.168.1.15 with the subnet mask 255.255.255.0, and it needs to send data to 192.198.45 and 10. It would first need to determine whether the target system exists in the same network or not. It would do that by looking at the subnet mask to compare the network ID. And if the network ID is not the same, then it would need to send the data to the router and be able to forward. So in this case, where if the subnet mask is 255.255.255, as it is a Class C address, so we would have network, 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 and then the host is 28, then it would then identify what that part of the network that the other system existed. So now the comparison for the last octet here to this, the 1 is different than the 10. So as the network IDs are different, it would know that the computer 2 is on a separate network, not in the same network. Now, if the second system is a .1 here, then it would be exactly in the same network, while they both have the same exact subnet mask. So when you look at computer 1 and the computer 2, first it's going to compare the subnet mask, then it's going to see if there's a matching network ID, if it's exactly the same. Now, if it's different in this case on the third octet, it would know that this is a different network than this one. So therefore, we would need to route. For the default gateway, which we often refer to as a router, this is a system that's going to help determine the destination of or the receiving system, whether it's on the same network or not. Now, this system must then pass the data to the router. Sometime itself is a router, so that way it would send the data to the system that is not on the same network. So how does it really know who is the router? And the default gateway is the IP address of the router, then it would use the IP address to communicate with external networks such as other networks in the internet. And so you would need to be including the gateway in your IP configuration, as we've done in the first lab. Now, when the system receives your configuration in IP address, it converts everything into binary. So all your decimal value, which is what you see as counting number normally, would then need to convert to 0 and 1s, which is in binary. And for a binary representation of your IP address, it would look something like this, even though it's still going to be in octets as in 8 bits for each. So when we see as an IP address, the system would see it as 0 and 1s like this. So you would have 4 sets of 8 bits that would be 0 and 1s, or in binary, and that will be your 32-bit IP address. So how does it do the conversion? Now, in decimal equivalent, we would start with the rightmost hand side. That will be your least significant bit. And as we move to the adjacent bit, your decimal would be multiple of 2, because there are 2 numbers in the binary. So on the first bit, your decimal would always be 1. On the next bit to its left, which is the second bit, we would have the decimal equivalent as 2. And subsequently, we would take the previous value and multiply it by 2, or 2 to the n, which gives you 1, 2, 4, 8, 16, 32, 64, and 128 decimal equivalent represented in the 8 bits for the octet. So this scale will always remain the same, as in it would be multiple of 2 for the decimal equivalent for every single bit that is represented from the least significant bit from right going into the left, and the most left is going to be the most significant bit, your MSB, and that will be bit 8. So when you look at the binary equivalent, when we have 192 in an octet, how does it represent 192? That will be 128 plus 64. So the bit 8 and bit 7 will be on, and the rest will be off. So to convert this, what we would have is we can use what's called an addition method. So we would have the first bit, which is equivalent to 128 here as bit 8. And the next bit is bit 7. That will be equivalent to 64 in decimal. And as you add this up, you would have 192. So for the address 192.168.0.x, the first octet would be represented as 1, 1, and the rest are zeros. So to convert a decimal to the binary, we would first use the decimal equivalent scale. The least significant bit is always on the right-hand side, and it's always going to be 1. The subsequent bit has the decimal value that is 2 times the previous. So what we can do is we can subtract the decimal equivalent and place the bit 2 on, continue to subtract the decimal equivalent until the remainder is 0. So if we want to convert the 192, we would then need to subtract 192 with 128, and we would place that bit on. And then we would subtract it again, 64 minus 64, we would place that bit on, and then we were left with 0. And the rest, we would fill in the 0 for the subsequent value. So in this next question, We would then answer and eventually need to convert the decimal to binary. So for question 5, it asks you what configuration is needed for the system to communicate to the internet and other network. You would need to have system IP address, which will be unique for that system, and it would contain network ID and host ID. It would also need to have subnet mask and default gateway IP address. Now to convert 172, which is a decimal value, into binary, we would use the following table. So when you look at this scale is always going to be the same starting from the right to left. That will be 1 times 2 would be 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32, 32 times 2 is 64, and 128. The largest number that we can subtract in this scale is 128. So you would start with that number. So you would take 172 minus 128, which gives you 44. So if we take 12, so that would be 4, so 44. So as you subtract 128, you would put a 1 at the top. And then we would take 44. As 44 is less than 64 here, we cannot subtract it, so we would put a 0 there. Then the next number we can subtract with is going to be 32. So we would then take 44 minus 32 is going to give us 12. So as we subtract 32, you want to put a 1 there. 12 is less than 16 on our scale, which is the next number. So you cannot subtract it. You would put a 0. Then the next number we can subtract 12 is going to be 8. So we would take 12 minus 8, which gives us 4. As you subtract 8, you would put a 1 there. Then next, we are going to take 4. 4 subtract 4 is going to give us a 0. So we would put a 1 there. And then the rest, we would fill in 0. So 172 is going to give us 1, 0, 1, 0, 1, 1, 0, 0. So 172, which is a decimal, it's a base 10 number, is going to be 1, 0, 1, 0, 1, 1, 0, 0. So this is the subtraction method. You would start out with taking the decimal value using the decimal equivalent scale. You subtract the largest number on that scale. Your remainder is going to then, as you subtract it, you would put a 1 at that position of the bit. Then you would take the remainder and you keep subtracting the next number. If the next number is larger than what you have as the remainder, you would put a 0 and move to the next number. And as you subtract that number, you would then put a 1 at that position, find the remainder, and you would continue to subtract until you reach 0, which is nothing left. And as you complete the subtraction method, if you reach the 0 before the last bit, you would then fill in the 0 for what's left. So we're going to go ahead and try another one. Here we're going to convert 255 into binary using the table. So we would start with 255. And the largest number we can subtract is 128 on that scale. So as we subtract 128, we would have, so 7, 30, so 137, or I'm sorry, 30. Yeah. So 15 minus 8, we would have 7. 5 minus 3, we would have 2, and then 127. Then as we subtract that value, we would put a 1 there. And then 127, we would then subtract the next number, which is 64. As we subtract, we put a 1 there. And so for 127 subtract 64, we would be left with 63. And then we would subtract the next number. So 63 minus 32 is going to give us 31. And then we would continue. 31 minus the next number, which is 16. So as we subtract 16, we put a 1 in that bit position. And that will give us 15 left. And then we would take 15 and we subtract the next number, which is 8 at bit 4. So as we subtract 8, we put a 1 there. And that will give us 7. Then we would take 7, subtract 4. You would have a 3 left. Put a 1 there. And then the next number we're going to subtract is 2. So 3 minus 2 is 1. You will put a 1 there. And then lastly, we are going to take a 1 minus a 1 is going to be a 0. So as you can see, when you have 255 for your octet, the 8 bits are all on. So that when we have 255, and if that's a decimal, then we know that all our bits are on. Okay. So for number 7, just like before, we would go through the decimal equivalent scale and we would subtract. And we would take the remainder and we keep subtracting until we get a 0. As we subtract that number, we will put a 1 in that bit position. For the next one, we would then convert 127 from decimal to binary. So you would start with 127, and since 127 is less than 128, it cannot subtract, so you will put a 0 there. It's less. The next number we can subtract is 64, so we can put minus 64, and as you subtract that, you will put a 1 there. So that will give us 63. Then on the next number is 32. You would take 63 as our remainder. We would take 63 minus 32. And here we would have a 31 left. And 31, the next number we want to subtract is 16 on the scale. So 31 minus 16, we would have 15 left. And the next number we can subtract 15 from, so we would do 15 minus 8, which gives us 7. And as you subtract 8, you put a 1 there. And 7 minus 4 is going to give you a 3. So as you subtract 4, put a 1 there. And then we're going to subtract the next number because 3 is larger. So let me move this down. So on the next number is 2. We're going to take 3 minus 2 is going to give you a 1. So put a 1 there. And then lastly, a 1 minus a 1 is going to be a 0. We subtract a 1, so we put a 1 there. So for 127 in decimal, we know that all 7 bits are on, and the only one that's off is the leftmost bit. So for 127 decimal, that will be equivalent to 0, 1, 1, 1, 1. Okay, in binary. Another way that you can check this is when you use Windows Calculator, there is a mode called Programmer. And when you enter the decimal value, you click decimal and you would put 127 and you would click binary. And so as you can see, we would have our answer matches. Now the output here, it doesn't show the 0, but you can see that it shows the same there. So you can use your programmer calculator to check your answer. Now to go in reverse, when we convert binary to a decimal value, what you can do is you can place your binary into the table, the scale, and then you're going to add up the decimal equivalent at the bit position that is on. So let's look at the example in the notes first. On the notes on page 3, it shows you that to convert the binary to decimal, you would place each binary value on the decimal equivalent scale, with each binary on each bit starting with the right, the most right. So we would put the 0 here, and then we're going to move left, so you put all your binary here. And then what you're going to do is you are going to add the decimal equivalent at the top for only if that bit is on. So in this case, if we have 1, 1, 1, 1, 1, 1, 0, 0, we would add the 1 here is equivalent to 128, so we would take 128. The 1 here is going to be equivalent to 64 plus 64. The 1 on the 6th bit, that would be equivalent to 32. We would add 32. And then on the 5th bit, we would add 16. And then on the next bit, bit 4, that's equivalent to 8, add 8. And then on the next bit, bit 3, equivalent to 4. And we would stop there because the last 2 is off, so we don't add those. So we would have 252. So in the next question, you would take this and you would place it into your decimal equivalent. So we would start with the 0 here on the right, and then the next 0, and then the next 0, and then we would go with this one for bit 4, and bit 5 is 1, 6 is 1, bit 7 is 1, and bit 8 is 1. So now what we're going to do is we're going to only add the one, the bit that has ones. for decimal equivalents. So we are going to add 128. We're going to add 64. We're going to add 32. We're going to add 16. We're going to add 8. And that is it. We're not going to add the rest because they are off. So you would take 128 plus 64 plus 32 plus 16 plus 8. And we can use our calculator. So 128 plus 64 plus 32 plus 16 plus 8. That will be 248. And that will be your decimal. So this binary that's given here is equivalent to 248. Then on the next question, it asks you to convert this binary value to a decimal. And just like what we did previously, we would place this into the scale here. So that will be 1. And the scale is always going to be multiple of 2. And then the rest, we have 0, 0, 0, 0, and 0. And as you notice that the last 3 bits on the right are on, so you're going to add those 1, 2, and 4 as those are on here. So we're going to add these, and that's going to give you 7. So 4 plus 2 plus 1 is going to give us 7. So this binary value here is equivalent to 7 base 10, which is your decimal. So for your future quiz and test, make sure you know how to do binary conversion as IP address. Uses decimal value, but the computer converts that to binary. For number 11, we would use the same technique. So you would then place the binary value into the scale. And then you're only going to add the value that has the 1, which is bit 8 and bit 1. Both here. So that means that we're going to add 128 plus 1, which gives you 129. So this binary value is equivalent to 129 decimal. So this gives you a little bit of practice on how to work with binary conversion from binary to decimal and decimal to binary. And this concludes my part 1 of the lecture. I will continue in the next part talking about IP address classes.